SpaceX did something unusual with Raptor 3's fuel lines, and it shouldn't work. This engine weighs just 1,525 kilograms, lighter than the version before it, yet it still produces 280 tons of thrust. Normally, less material means less strength. So how did SpaceX break that rule? The answer isn't in the metal. It's in how they stopped building the engine and started printing it instead. Here's what that actually means. Here's the problem SpaceX had to solve. For decades, rocket engines have been the slowest part of building any rocket. Not the tank, not the hull, the engine. Each one is a maze of thousands of fuel lines, sensors, valves, and manifolds. Traditionally, skilled technicians spend months welding and bolting all of that together by hand, one joint at a time. Think about what that means in practice. You can build a rocket's body in weeks, but if the engine takes months, the body just sits there, waiting. The fastest part of your factory is only as fast as its slowest part. That's not an opinion. That's just how assembly lines work, whether you're building rockets or cars. So if SpaceX wanted to build Starships the way Tesla builds cars, on a line, at scale, they had one massive obstacle standing in the way. Raptor, the engine. Raptor 2, the version flying on most Starships until recently, still looked like a traditional rocket engine, covered in exposed plumbing, external tubing, bolted joints everywhere you looked. Beautiful engineering, but slow to build. Painfully slow. Now, let's talk about why that had to change and how SpaceX changed it. Not by fixing the engine first, but by rebuilding the entire factory around it. The ugly years were the point. Rewind to 2019 and 2020. If you watched the early Starbase live streams back then, what you saw looked almost embarrassing. Workers manually running flux-core arc welding torches in the open Texas wind. The prototypes that came out of that process looked like dented, crinkled water towers. Fans joked about it, critics mocked it. But that rough, ugly phase wasn't a failure. It was a deliberate decoy. SpaceX needed to lock in one critical number first: the exact structural dimensions of the 9-meter stainless steel ring that would become the backbone of every Starship and every super heavy booster ever built. You can't automate a process until you know exactly what you're automating. So the crude welding phase existed to finalize the geometry. Once that number was locked, everything changed. SpaceX sealed off the entire manufacturing pipeline into a massive, climate-controlled structure. No more open-air welding in coastal wind and humidity. Why does that matter? Because moisture, salt air, and wind shear are exactly the conditions that introduce tiny pockets of porosity into a weld. Microscopic weaknesses that can turn into catastrophic failures under the extreme pressure of spaceflight. By sealing the environment, SpaceX eliminated an entire category of failure before it could happen. Inside that fortress, the philosophy flipped completely. Rockets stopped being stationary objects that workers climbed all over with scaffolding. The factory became a living conveyor system. Steel sheets roll in. Automated stations form them into rings. Robotic megabays rotate massive hull sections with sub-millimeter precision. That still leaves one question unanswered. How do you join 9-meter steel rings fast enough to keep up with that kind of speed? That answer is where things get genuinely strange. A laser that vaporizes its own path. Traditional aerospace has two main options for joining thick metal sections: multipass arc welding, slow and requiring layer after layer of melted metal, or friction stir welding, incredible technology, used on things like the space shuttle's external tank, but mechanically brutal, demanding massive physical force and heavy backing jigs just to push through the joint. SpaceX decided neither was fast enough, so they built something else. High-power automated laser beam welding using a mechanism called keyhole welding. Picture it this way. A normal weld melts metal from the surface down, layer by layer, over multiple passes. That exposes a wide area of metal to heat for a long time. A keyhole weld does something completely different. A tightly focused, multi-kilowatt laser beam instantly vaporizes a tiny hole straight through the joint, all the way through the thickness of the steel in one shot. That vapor cavity becomes a channel, carrying the laser's energy through the entire seam at once. As the robotic arm glides along the ring, molten metal flows in behind that moving hole and solidifies into a deep, clean joint. A process that used to take hours, sometimes days, gets compressed into minutes. That speed creates a second, less obvious advantage. Every weld generates heat, and that heat spreads outward into a zone around the joint called the heat-affected zone. In slow, traditional welding, that zone gets large, and the extended heat exposure changes the microscopic crystal structure of the steel, making it weaker and more brittle. To compensate, engineers have always had to make the surrounding metal thicker just to survive the loss of strength. Thicker means heavier. Heavier means less payload to orbit. Because SpaceX's laser moves at several meters per minute, the heat gets applied and gone almost instantly. The heat-affected zone shrinks to something microscopic. The steel right next to the weld keeps nearly all of its original strength. That lets SpaceX drop the hull's steel thickness from 4 millimeters down to 3, 1 millimeter. That's it. But across a 50-meter tall ship and a 70-meter tall booster, that 1 millimeter strips out roughly 20% of the entire airframe's mass. In a business where every kilogram saved is a kilogram of cargo gained, that number is enormous. Speed and thin walls create a new problem, though. What happens when the weld itself isn't perfectly smooth? The step. Everyone else skips. Even a flawless laser weld can leave behind a microscopic ridge, a tiny distortion right where the two sheets fuse together. In traditional aerospace, someone would grind that down by hand. Slow, imprecise, and it tends to shave metal unevenly, right in the one spot you can least afford to weaken. SpaceX replaced that step with automated planishing. Directly behind the welding head, high-pressure rollers clamp down on the fresh seam and physically hammer it flat under enormous force. This does two things at once. It eliminates the tiny surface irregularities where stress could concentrate and eventually crack, and it cold works the steel, realigning its internal crystal structure so the weld becomes as strong or stronger than the metal around it. This is also where that smooth, mirror-like finish on modern starships comes from. And that finish isn't just for looks. It reduces aerodynamic drag during the violent heat of re-entry. This is also where SpaceX diverges from basically every legacy aerospace company on Earth. In traditional manufacturing, inspection happens after the fact. Weld first, then roll in a massive X-ray or ultrasound rig, scan the section, and wait days for inspectors to review the images by hand. If something's wrong, the entire production line stops cold. SpaceX doesn't wait. High-frequency digital sensors are mounted directly onto the robotic welding arms. As the laser moves forward, those sensors scan the molten pool and the solidifying seam, millimeter by millimeter, in real time. Custom computer vision models analyze the thermal signature, the acoustic emissions, even the internal density of the metal as it cools. If a microscopic defect starts to form, the system catches it instantly and adjusts on the fly. By the time the robot finishes its pass, that section of hull is already structurally certified, not tomorrow, the second the weld is done. At this point, SpaceX has solved the hull. They can build the body of a rocket faster than anyone in history, but a fast hull means nothing if the engine bolted onto it still takes months to build, and that's exactly the wall SpaceX ran into next. Steel rolls in one end of the factory, and a fully welded, inspected hull rolls out the other end in a fraction of the historical time. But Raptor 2 still belonged to the old world. Thousands of individual components, tubing running across the outside, bolted joints everywhere, each one requiring careful manual assembly. A hull built in days sitting next to an engine built in months. The line could only move as fast as its slowest station, and that station was still the engine. So when SpaceX unveiled the production version of Raptor 3, it wasn't a routine upgrade. It was a redesign built around one question. How many separate parts and welds can be eliminated entirely? Set the two engines side by side, and the difference is immediate. Raptor 2 is layered in visible tubing and joints. Raptor 3 looks sculpted, like it was carved from a single block of metal. In a very real sense, that's exactly what happened. The engine that gets printed, not built. Instead of manufacturing thousands of individual components and joining them one by one, SpaceX uses direct metal laser sintering to print entire subassemblies as single, solid structures. Internal plumbing, propellant passages, the regenerative cooling channels that keep the combustion chamber from melting itself, all of it built directly into the walls of the turbo pumps and combustion chamber as the part is printed layer by layer. No external pipes bolted on afterward, no welds joining dozens of separate tubes together. Every weld in a traditional engine is a potential failure point. Every joint is one more place a leak could start, one more spot needing its own inspection. Raptor 3 doesn't eliminate those risks through better testing. It eliminates them before manufacturing even begins, because the parts that used to be joined together simply don't exist as separate parts anymore. Now, the paradox from the opening comes back into focus. This engine comes in at roughly 1,525 kilograms, lighter than its predecessor, while still generating close to 280 metric tons of thrust. In almost every engineering discipline, removing material means losing strength. So how does an engine get lighter and still hit the same brutal thrust number? SpaceX isn't breaking that rule. They're sidestepping it by removing weight that was never structurally necessary in the first place. The bolts, the redundant tubing, the joints, the material that existed only to connect one separate part to another. When those connections disappear, so does their weight without touching the parts that actually generate thrust or contain pressure. One more advantage hides inside this design. The integrated cooling passages don't just keep the engine alive during ascent. They also let Raptor 3 survive the brutal heat of atmospheric re-entry without a separate external heat shield layer bolted onto the engine bay. One integrated system doing a job that used to require two. So what was Raptor 3 really built for? It's easy to assume this engine was designed purely to be more powerful, a better piece of rocket science, and it is all of those things. But that's not the primary force driving the redesign. Raptor 3 wasn't primarily engineered to push performance numbers higher. It was engineered to move through a production line at the same speed as the hull surrounding it. Every weld removed isn't just a safety improvement. It's a manufacturing step removed, one less thing standing between raw material and a finished, flight-ready engine. Raptor 3 wasn't designed for the rocket. It was designed for the factory line. That single shift changes what producing rockets means for SpaceX. Traditional aerospace treats propulsion as a handcrafted specialty, something that can't be rushed. SpaceX just built an engine that moves at the same pace as the airframe around it. When engine and hull share the same production timeline, you're no longer building rockets one at a time. You're building them the way a factory builds anything else, continuously, predictably, at scale. A good engineering story doesn't get to skip the uncomfortable parts. All of this precision, the laser welding, the real-time inspection, the printed engine internals, none of it makes a rocket immune to failure. Just last week, a Starship stacked with all of this technology came within 3 seconds of liftoff, before its automated systems detected that 4 of the booster's 33 Raptor engines failed to ignite properly. The system shut down the remaining 29 engines instantly, keeping the entire 5,000-ton vehicle safely on the pad. 2 of those engines are now being replaced before the next attempt. Even an engine built to be simpler, lighter, and faster to manufacture than anything before it can still fail as an individual unit. Precision manufacturing reduces the number of things that can go wrong. It doesn't reduce that number to 0, and Raptor 3 isn't the exception that finally makes it so. What it does change is what happens after a failure like that. When an engine is a single printed structure instead of thousands of hand-assembled parts, diagnosing and replacing it doesn't take the months it once would have. The same philosophy that builds these engines fast is the same philosophy that gets a fixed one back onto the vehicle fast too. That's Raptor 3, engineered for the factory floor, not just the flight. Thanks for watching the Space Brief. I'm Adrian. Like, share, comment, subscribe, and check the video on your screen now.